Hi everyone! In this video, we are going to learn about something very important in calculus, limits. Don't worry, the idea of a limit is actually simple. A limit answers this question. What value is the function getting closer to? Even if the function is not defined at that exact point. By the end of this video, you will understand what a limit means, why limits are important, and how limits connect to derivatives. Let's begin. In calculus, a limit describes how a function behaves as the input, usually x, gets close to a certain number. Notice something important. We're not asking what is the value of the function at a point. Instead, we're asking what value is the function getting close to. That is the key idea. Sometimes a function is not even defined at that point, but the limit can still exist. So when we talk about limits, we care about what happens as x gets closer and closer to a number, what value the function is moving toward. So why are limits important? Limits help us describe instantaneous rate of change, define the derivative, analyze the behavior near discontinuities. So if you understand limits, you are building a strong foundation for calculus. Let's think about this in a simple way. Suppose we have a function f of x. We want to know what happens as x gets close to a number. Let's call the number a. Now imagine this. As x gets closer and closer to a, the values of f of x get closer and closer to some number L. If that happens, we say the limit of f of x as x approaches a equals L. And this is the math notation for a limit. This means as x gets close to a, f of x gets close to L. Very simple. The limit looks at what happens near the point. It does not always tell us the value of the function at that point. That is very important. A function can have a limit at a point, but not be defined at that point. Or a function can be defined at that point, but the limit does not exist. The value of the function and the limit are not always the same. Let's look at the graph. Notice an open circle on the curve. An open circle means the function is not defined at that exact point. Now look at the curve. As x gets closer to that point from the left, the curve moves toward the open circle. As x gets closer to that point from the right, the curve also moves toward the open circle. So, what does that tell us? From both sides, the function is getting close to the same value. That means the limit exists, even though the function is not defined there. Now look at the dot. That dot shows the actual value of the function at that x. But notice, the limit is the value at the open circle, not the dot. That is a very common example in calculus. Let's review. A limit tells us what value the function is getting close to. It does not always tell us the value of the function at that exact point. A limit exists if the function approaches the same value from the left and the right. If the left side and right side go into different numbers, then the limit does not exist. So now that we understand what a limit means, Let's talk about how to estimate a limit. Sometimes we don't want to look at a graph. Sometimes we want to use numbers. And one simple way to estimate a limit is by using the table of values. Here's the idea. If we want to find a limit as x approaches a, we pick x values that are slightly less than a and slightly greater than a. Then we calculate the function values and we watch what number the function values are getting close to. That's it. We are checking what happens from the left, what happens from the right. If both sides move toward the same number, then that number is the limit. Now let's try an example. We want to estimate the limit of x squared plus 1 as x approaches 2. First, notice something. This function is f of x equals x squared plus 1. This is a polynomial function. Polynomials are smooth and continuous. But let's pretend we don't know the answer yet. We'll use a table to estimate it. We want to estimate the function value as x approaches 2. So we choose numbers close to 2. From the left of 2, we choose 1.9 and 1.99. From the right of 2, we choose 2.01 and 2.1. Now, we calculate f of x at each value. When x is 1.9, we'll substitute 1.9 in for x. 1.9 squared plus 1 is 4.61. So the function value at x equals 1.9 is 4.61. Next, when x equals 1.99, we substitute 1.99 in for x. 1.99 squared plus 1 equals 4.9601. Notice something? As x gets closer to 2 from the left, the function values are getting closer to 5. Now, let's check the right side. When x equals 2.01, I substitute x with 2.01 to find the function value. 2.01 squared plus 1 is 5.0401. When x equals 2.1, I substitute x with 2.1. 2.1 squared plus 1 is 5.41. Let's look at all the values. From the left, we get 4.61 to 4.9601. The function values are getting closer to 5. From the right, we get 5.41 to 5.0401. They are getting closer to 5. From both sides, the function values are getting closer to 5. So we can say, as x approaches 2 from both sides, the function values approaching 5. Therefore, the limit of x squared plus 1 as x approaches 2 is 5. Notice something interesting? For this function, f of x equals x squared plus 1, if we just plug in x equals 2 directly, we have 2 squared plus 1, which is 5. So in this case, the limit is the same as the function value. This happens because the function is continuous. But remember, this is not always true. So that's why learning how to estimate using a table is important. Using a table helps us see what happens from the left, see what happens from the right, confirm that both sides go to the same number. If both sides approach the same value, the limit exists. If they approach different numbers, the limit does not exist. So far, we've learned what a limit means and how to estimate a limit using a table. Now, let's look at another method. Instead of using numbers, we can also use graph. A graph gives us a visual way to estimate limits. To estimate limit of f of x as x approaches a, we look at the y values the graph is moving toward as x gets close to a. Very important, we look at what happens from the left and from the right. And remember, the limit does not depend on the value of the function at that point. It depends on what the graph is approaching. Now, let's look at this example. We have a function g of x, and this is the graph of g of x. And we want to answer 3 questions. Take your time and look at the graph carefully. First question, we want to find g of negative 1. This question is asking, what is the actual value of a function at x equals negative 1? To answer this question, we'll look at this graph. When x is negative 1, the function value is here. So we look at the y value of this dot. The y value is 4. So when x equals negative 1, y is 4. That means when x is negative 1, the function value is 4. In point, when you see the filled dot, that gives you the function value. Second question, what is the limit of g of x as x approaching negative 1? We are not looking at the dot here. We're looking at the curve. Negative 1 is here. I draw the line at negative 1 so that you can see the left and the right clearly, but you don't have to do this. This side is the left side of negative 1, and this side is the right side. Now, we ask ourselves, as x approaching negative 1 from the left, what y value is the graph approaching? And as x approaching negative 1 from the right, what y value is approaching? So look carefully. The graph moves toward the open circle from both sides. So at this open circle, what is the y value? The y value at the open circle is 3. That means as x approaching negative 1 from the left, the graph is approaching 3. And as x is approaching negative 1 from the right, the graph is also approaching 3. So the limit when x approaching negative 1 from both sides is 3. Notice something very important. The dot and the open circle are at different heights. That means g of negative 1 is not equal to the limit of the function when x approaches negative 1. Now, the final question. Is g of negative 1 equals to the limit of g of x as x approaches negative 1? No. This situation is called a removable discontinuity. The graph has a hole on the curve. The function is defined at that exact x value, but not at the point the curve is approaching. This is a very common example in calculus, and it shows us something important. The limit depends on the behavior near the point, not the actual value at the point. So when estimating limits from a graph, look at what the curve is approaching. Check both the left and right sides. Ignore the fill dot when finding limit. The function value and the limit are not always the same. If both sides approaching the same number, then the limit exists.